I understand the slide set is visible, but someone should start recording. Okay, thanks. So today we'll discuss on a new topic, and that is artificial neural network. Uh, this you can refer to these chapters for this particular topic. Like you can check the chapter 6 of the book by Duda, Hurt, and Stork, and then chapter 11 of Ethan Alpezian's books, and chapter 4 by Tom Mitchell's book. So we discussed earlier in while discussing about the linear discriminant analysis or linear discriminant classification. There we can see that a linear discriminant classifier, particularly two-class classifier, that can be also modeled as a in a graphical form, and where the processing is done at a node, and that node is known as perceptron, which has the input feature vector and a weighted combination of the input feature vector plus a bias term W naught. So you get that summation. That is the linear uh, computation of the linear functions. And then after that, uh, as we have seen that depending upon the sign of the um, sign of the value, we classify it either to class. I mean, there are two classes, so each corresponds to one of these signs, either positive or negative. Basically, you are finding out an hyperplane which is partitioning the feature space into two regions. One region corresponds to class 1 and another region corresponds to class 2. Now, this processing is modeled in these computations, as you can see here. Uh, say, first, this is the input feature vector. So you get an weighted combination, and then you add the bias term. You remember that actually we had in the previous discussion that we have another input with a constant value 1, and then the bias is also incorporated into the same form of the weighted combinations. So we can also write in this form. And so these are the parameters. These are the parameters. These weights and the bias, these are the parameters. And then this value is processed. That means there is a function which will check, which will provide you the finally the it's a nonlinear function which will give you the output from this value. And this function we have used the sign functions in the previous example, like 1 and -1. Or you can also use other kind of functions, like instead of having discrete values, you can have continuous values. That means a nonlinear value where you can see that this is a sigmoid function. This function is a sigmoid, or sometimes we also call it logistic function. So this is a functional form, and it tries to resemble the similar response. The advantage here is that it's a continuous function. So it is derivable at every point in its functional space. So that is the advantage. In fact, the derivatives is also very interesting for the sigmoid functions, that we'll see that from the functional value itself, you can compute the derivatives. Right? So uh, so this is the computational node for two-class classification. But one of the kind of model in that when we say a network of these kind of nodes, which actually tries to mimic which is inspired by these biological connections of neurons in our nervous system, and that is how the name came. This neural network, or you can call it artificial neural network to just distinguish from the biological neural network. So there you can see very strong similarity of the computational model, what is being done. So this is that perceptron node, and these are the corresponding inputs from different, these are the input sensations, and they are weighted input value, and there also some nonlinearity function is there, like sigma. There is a concept of action potential. When the potential is sufficient, then only this neuron fires. So if you go through the biology of neural firing, it's very interesting. And the other part is that this sensation is carried out, and then again, it is also you know, uh, it is also stimulating other neurons, and they are connected. So it's a network of neurons. So the same unit is repeated, and they are connected. So from this output can go to, in fact, various other neurons with again that weighted combinations as well as mentioning. And so the connection of these kind of nodes that provides you neural network, and we can also say network of perceptrons because we named it perceptron. So it's a very powerful model for describing input-output relations. So when you are modeling input-output relations, you know that even the classifier is also a model for input-output relations, where output is the class level and input is the feature vector. And in general, any function models that input-output relations. And there are other techniques like regression techniques where, given the input-output values, you develop a model. So neural network can be considered from that perspective. So you have a model here, mathematical model, and it's very strong model means it can handle very large varieties of input-output relations. So every model has its limitation, we know. We have discussed earlier also, like we have to choose the appropriate complexity of a model, etc. So all those things are also valid in this case, but the framework is very powerful. So under the same framework, you can express various types of functions with high accuracy. So this is, in a nutshell, this is the kind of descriptions. As you can see that I have shown the repetitions of the perceptron nodes and their connectivities in this form. So in this case, input is a vector, a feature vector, as you know, and even output also could be a vector. Or it could be a scalar if it is only one output node. It could be a scalar, or it could be a collection of output nodes, set of nodes, and each is also representing a field of a vector. So the popular network what we mostly deal with is the feed-forward network. And in the feed-forward network, there is no feedback from the layers. Like this kind of feedback is not there. And particularly, we call it multi-layered feed-forward because as if the connectivities are in stages. So from one layer, the outputs are connected to the inputs of the another layer. So a layer consists of a set of perceptrons or set of neurons, and the outputs of all those responses are connected to the input to the neurons of the next layer. So that is how the layers are defined, and since we have more number of layers in this kind of connectivity, we call it multi-layered. The term feed-forward comes because there is no feedback from the output side towards any input node. And there is another term called fully connected, which means that every neuron of a layer is connected to every other neuron of the next consecutive layer. So then we call it fully connected layer. So just some technical terms, as you can see that input layer itself is the input, what you are giving. And then the output layer is the output neurons, of course. And then the hidden layer is the, I should say, it is the first layer. We call it first layer because input is already as a node. As you can see here, this is what we are considering the inputs, and that's also represented input layer. Whereas output layer is right. This is called output layer, which is output responses. And then hidden layer 1, hidden layer 2. In this way, we are referring it. So it is important to understand the terminology because later on when we discuss, the meaning of ith layer should be clear to you. So this is how we are describing. So the processing is a layer-wise processing. So ith layer takes input from the I-1th layer and forward shifts output to the input of next layer. And as I was mentioning, we are considering here fully connected feed-forward network. There could be sparsely connected feed-forward network also. So just to have some mathematical description of this model, how we can denote this particular computational model. Let us consider the jth neuron of ith layer. You use this notation. Okay, I hope the notation is clear to you, because you know that every layer consists of a set of neurons, and every neuron we are identified by a kind of index, so that for the sake of description, that is convenient for describing the operations. And similarly, the corresponding weights, that means the weights of the connectivities, you have to identify the edges, which means each weight corresponds to an edge, which is a connected, which edge is defined by the connections from output of one neuron to the input to the another neuron. So we denote it in this form. Okay, so Wji, we denote it in this form. As you can see that every since it is fully connected feed-forward network that we are considering. So for the ith for the jth neuron of the ith layer, I is a subscript here. There are from this node, actually we are defining this weight with respect to its input weight. So if this is the ith this is the ith layer and this is the jth neuron. So all these weights, these weight vectors are denoted by Wj. So that is how. So that means there are, that there are ni minus 1. So every, its previous layer is I minus 1th layer, and we assume that there are ni minus 1. I mean, the subscript is something like this. Because of some problem, I have to denote this subscript in this form. So from the ni minus 1 number of output nodes are there in the I minus 1th layer. From each, there is a connectivity. So that is how this weight vector is defined for a particular layer. And also the bias term also involved of that node. So bias term is denoted in this way. So that with the 0th subscript for the jth node. So that is how. And ni minus 1 is the dimension of input to the neuron. That means you understand that it is basically the weight vector, the dimension of the weight vector. So that is what. And ni is the dimension of the output at the ith layer. So it corresponds, right? So from the ith layer, there are ni number of nodes. In the ith layer, there are ni number of nodes. So finally, if I consider the output of the neuron, so we may write the output for this particular node, which is denoted by ne subscript j superscript I. So we are also denoting the output as, so outputs are denoted by the symbol y with subscript j, that is the jth neuron of ith layer. So you can see that the same computations we are expressing here, like it is the weighted combination of the input from the what is obtained from the I minus 1th layer. So that is, so its dimension is also, and this is the, yes, any question? Any question? Okay, maybe there is no question. So in this way, the input-output relationships are expressed. It's in a particular neural node, and as you understand that a output vector from the output of that ith layer, you get ni number of such functional values. So output of jth neuron in the ith layer is given in this form. So I can write the input-output relationships in this form, right? So so Z is the output. As you see that in the perceptron node, each Z is a weighted sum, and then you apply the functional values. So this is what is Zi. Right? The vector of this. So this value, it is basically expressing a vector of these values we are considering, that is the capital Zi. And then finally, we are applying the corresponding nonlinearity with this. So we write all these vectors in this form. This is the bias term, and these are the weight vectors. So each row represents the input weights of the corresponding node at the ith node of that, or jth node of that layer. Each row corresponds to that. But you have the fixed set of input vector from the I-1th layer. So this is a matrix. So what is the dimension of this matrix? Can anyone tell me what is the dimension of this matrix? Is there any, what is the dimension of this weight vector?
Sir, Ni cross Ni minus 1.
Yes, that's right. So that the dimension of the matrix is Ni cross. Let me so let me use subscript only. I have used that hyphen because I had some issue with representing it. So Ni cross Ni minus 1, because dimension of each row is Ni minus 1. That is the dimension of the weight vector to an input node. Whereas at that layer, there are Ni number of neurons. So you have Ni number of outputs. So of course, here we are just expressing the linear part of the operations. Then you can apply the sigmoid operations. So nonlinearity. So this is what the nonlinear part is expressing. So the same thing, as you can see finally, that this is the notations we are using. So we are using bold font just to note that that is a kind of pointwise operations of a vector operations or functional operations in this case. So this is how we are describing it. And finally, a multi-layered feed-forward network can be, and also fully connected, as you see, that can be modeled in this form. That means you have an input, then there is a, these are the parameters. So if I specify this, it specifies the model completely. And this is how the computation takes place. Is there any questions regarding this? So you understand now that if I give you the input-output relationships, your objective would be to estimate these parameters so that it tries to maximally fit the input-output relationships, which means now you define an objective functions like mean square error objective functions, for example. So if you use mean square error, you would like to derive those weights. You would like to derive those weights for this model, or find those weights for this model, which will minimize that error function. So that is the optimization problem that you need to solve for designing a neural network. So this is what now we have. So the whole thing, let me express as the parameter W. All these parameters, as you understand, every layer has certain number of parameters, its weight vectors and biases. So bias vector and weight vectors for each node. And then this is how we can represent this model. So in an abstract form, we just represent the neural network, artificial neural network, as the model whose parameters sets is represented by W, and which takes the input feature vector X and provides an output feature vector, say, in this case, it is represented by O here, Xi and Oi. So the problem is that if I give you this set of values, that is corresponding input output values for n data points, you have to find out the parameters which will, which will produces the outputs given that input xi for all I. So naturally, it is it is not possible to get a consistent, um, consistent model in this case. Uh, I mean, the model is powerful, but still, in all practical cases, there may be some degenerate cases where consistent models are available. Uh, I mean, if it is completely linear and you know that apply the linear theory, and there are cases when you can get a model, consistent model. But in mostly this is not considered, which means there would be an error of approximation of this model. So that's why it has become, it is always posed as an optimization problem where you define an error function. So this is the error function most commonly used, which is the mean square error function. There could be other forms of error functions also. This is the error functions we will be discussing here. In fact, we are considering these error functions for linear discriminant classifier also. So we have used this particular error function there also. So you can see that it is square of the norm of the vector of the differences, which is effectively, this is what is the mean square error, what we consider in this case. So the same approach of gradient descent procedure we'll be following here. That means we can start with an initial set of weights, and then you move towards the steepest, opposite to the steepest gradient in the parameter space. So computation of gradient is the is a major, I should say, challenge, or that is the major task of this optimization problem. Because as you see that since your model is quite complex in the sense it's a network of perceptrons, so there has to be some systematic way you should compute these gradients. Now, in many cases, what happens that empirically this gradient is computed. In some very complex models, what we do, let me just explain what is this empirical means. So suppose you have a model, that means model is described exclusively by the set of parameters, and you need to compute gradient, means you need to compute the corresponding the functional value. So this is a functional f, so you need to compute the gradient of f with respect to w, right? You need to compute the, sorry, it should be there, gradient f with respect to w. And yes, so we can write like this also. There are different ways. You can usually the partial derivatives are written, and in the multi-parameter space, it is written in the Jacobian, in the matrix, in the Jacobian form, and many other forms. So just intuitively let me understand that what you are doing, that you are trying to find, which means that, so mostly what you are computing the gradient, since it's multidimensional, you are computing the partial derivatives of this function with respect to one of the component of the weight vector, right? So let us consider the whole parameter as a, you can just represent it as a linear vector, as a flattened vector, and say I is the ith component of that vector. So you are computing this. So what we can do that, suppose you consider a particular value of wi and keep other fields of w as a constant, or you find out a value, and then you add a, you make a delta increment of that value, very small increment of that value, and also you compute the value, and then you can find out the differences, and from there you can compute the derivatives, partial derivatives. Now this is the empirical way of computing. So one can do that. One can do that for a complex model, but as you can see, it is very computationally intensive, and because at every point you have to compute. If your w is a very the dimension is very high, that if your model is large, w could be in today's deep neural networks context, W could be millions. Huh? So there, this kind of computation is not practical, not practical. So though this is one way you can compute the gradients vector, and then you can apply this gradient descent procedure, but this is not practical. For a small model, you may do it. Okay, so the algorithm which actually uh, you know resolves this particular issue and which is very much applied, uh, that is the backpropagation algorithm for computing this gradient. We will be discussing that. But just to give you the overview of this gradient descent approach, once again, the approach is same. You start with an initial W naught, update W iteratively. So this is how you will do it. We are expressing here grad of function, gradient of f. That is a gradient vector with respect to W. And you know that if I take partial derivative, this is how the partial derivative has to be computed. Finally, you have to compute the functional partial derivative with respect to function. That is a functional model. So this part, these computations I was talking about, and these computations, empirically, if you do, it is very, it is very intensive. And you can use also stochastic gradient process descent, which means you could have done the batch wise, the whole batch, or you can use at every sample you can do it. You can do mini batch wise, that there are, all these are possibilities. So these are just, showing you that what are the flexibilities are there in these computations. You can immediately update the weights, or you can compute the gradient or compute these gradient values for a certain set of samples, and then you sum them and you update the weight. There is a step size which is also involved, as you can see. So we will be discussing about this backpropagation algorithm for computing gradient now. As just I just gave you the motivation why we require that kind of algorithm. So the in the principle of behind this backpropagation algorithm is that chain rule which is used for computing a gradient. So when you compute the gradient of a function, so function of a variable, so you know that first you have to determine the gradient of that function with respect to the, suppose it is fz, so you determine the gradient f with respect to z, and then again z is also a function of x, then you multiply it with the gradient of z with respect to the respective input variable. So finally, that is a terminal variable, free variable. That is what you are using. So there are dependent variables and there are independent variables. So when you are expressing them in this form, so it comes so as if so, which means that if I apply chain rule, I will be first determining the gradient of this particular. So I will determine the gradient delta O delta Z, and then I will determine the gradient of, at this point of delta Z and delta X. So that is how you get the gradient from delta O and delta X. So this is a gradient vector I just show you. And one thing you should also note that even there is an error term. So before delta O, delta Z, I have to compute also delta E, because finally I have to compute the partial derivative of error with respect to individual components. So I need to compute actually delta E, partial derivative of E, and delta W, one of the components, like to get this gradient vector, right? So for that delta E, delta O, which is in this case we can see that it's quadratic function, so it's very simple, like twice of t minus O. In fact, to cancel 2, sometimes we take the function as half of t minus O whole square. That is, in many cases we do it so that the gradient becomes that 2 gets cancelled, and it's simply the gradient is minus of t minus O, because there is a negative sign. So that would come, right? So let us see how this computation proceeds. So as I was mentioning, you have to compute like this. That is the chain rule. If you are computing partial derivative of v with respect to wi, you have to compute the derivative with respect to the output O, then again derivative of O with respect to the z, and then derivative of z with respect to wi. So each you can compute, right? So one of the advantage, if you have sigmoid function, particularly this one, if you have a sigmoid function, you have an advantage of computing this gradient. We'll see that also. So in this case, it is minus twice of t minus o. I have taken t minus o whole square, so it should be minus twice of t minus o. This I am just expressing a prime z, or that is derivative of that function. Depending upon the function, this derivative needs to be computed. And as you know that already the linear relationships between z and xi is already there. So you simply get the input xi, right? So that is how you get it. You can write it in this form. So the function can be written in this form. And so it's for a single perceptron we are discussing. So I was telling you that what is the advantage if you have the sigmoid function. This is the advantage. Like the derivative, what you compute at z for the sigmoid function, you just compute using the functional values like fz into 1 minus fz. That would give you the derivative. So your computation system, if you know the functional values, you can compute. Similarly, you may have to compute also this, because you know that when you are computing the here xi is an input. Now it's for a single perceptron. This is of course the terminal input, but if it's a network of perceptrons, then some of these inputs are also needs to be, now you have to compute the derivative with respect to that input, um, because these are dependent variable of the of the other variables from the side of the input, right? So these two quantities you need to compute. So in this case, if it is derivative with respect to the input field xi, so there this is basically given in this form. So this is also another very simple but interesting feature that you observe, which we'll be using in the case of backpropagation control. One of the advantages, it's an analytical method. Analytical method in the sense that when you are computing this gradient, as you can see, I mentioned empirical method where you give a kind of stimulation and you compute the functional values. You change the corresponding parameter value and compute the functional values, and then you observe the differences, and from there you compute the gradient. But in this case, you do not require to do those things. Simply from that point value itself. So at that point, whatever the value of the target function t, whatever the value of the functional value o, the derivative of f, and also the weight parameter weight value. So all those values, and using those values itself, you are computing this derivative. And that is the advantage you have when you apply the chain rule. And this is what is used in the case of backpropagation. Right. So, so the heart of the backpropagation method is that we are applying chain rule from the output side, from the output layer towards the inputs, from output towards the input. So that is what you are doing. That means from output layer towards input layer. So compute partial derivatives of weights at I minus 1th layer from the ith layer. So that is what is your problem. Incrementally, that is what you are doing. So you compute partial derivatives of weights at I minus 1th layer from the ith layer. So we know all the partial derivatives till the response variables available at the ith layer. That means till the whatever outputs are available. So just to show you figuratively here, once again, I will give you one example here. You can see the connectivities. See, just these notations, let us once again understand. So this is layer 1. This is layer 1, as you have seen. This is layer 2, this is layer 3, this is layer 4. And the outputs in layer 2 is denoted by this, right? First neuron of the second layer. So this is the output corresponding to that. And you see that this is W312, 2 is the second layer, and 3 is the third neuron. Here is actually this W31 is with respect to this. So this is the third neuron of the first layer. So this is output is also denoted, and this weight corresponds to this. So this age. So W31 corresponds to this age, 3 and 1 connected, right? So we are also using superscript to denote, as I was mentioning, to denote this node, right? And 3 denotes the node of the previous layer. Okay, so as you can see that we are trying the gradient of error with respect to W312 at this point, for example, if you would like to compute this value. So what you should compute? You should compute like this is what we are trying to compute here, for example. So we apply delta E delta O here, first delta E delta O, then this output, derivative of this output with respect to these two, right? With respect to these two responses. Okay. So if you just look at which are the dependable things, or which are the variables which are getting affected by this dependent variable. So for W31, since this is connected to this response, so this will be affected. If I change W31, then since this is affecting these two, then these two values will be affected. So effectively, I have to compute the derivative with respect to with respect to this, and then what we'll be doing, we'll be adding them. So you are doing delta O delta Y13 plus delta Y13 delta Y12, right? So delta O delta Y13 delta Y13 delta Y12, and definitely delta E delta O, that would be this path. Through this path you are getting this gradient. Similarly, through this path you are getting delta O delta Y23. So this is Y23, and then delta Y23 delta Y1. Now this gets added here, accumulated, and then because Y12 is expressed as the I mean these two are expressed as the variable of Y12, so this gets accumulated here, and then we obtain the gradient of delta Y12 with respect to delta W31. So this is how the chain rule is applied, and this is how this computation is carried out, and you can apply the corresponding corresponding derivatives, because for each say this one Y12 to W31, you know the relationships there. Already we have discussed this. So this is delta Y12 to delta 31. So it means it should be no, it should be Y31. It should be Y. This is 3. As you have seen in the previous case, you see this value. This xi is the present. So we are computing this value actually at prime z, and this xi is the input towards that node. So there is an error. Since this is 3, it should be 3. Right. So this part is computed in this form, and similarly the others are also computed, like Y23 and Y12. The relationships are here. once again, it should be f prime z, and then this weight should be added. So I think those are there in the next slide. So we'll move to the next slide and we'll find out. So delta E delta O is this, delta O, I mean, these are the computations. I'm just showing whatever I've described. Right, so we are just trying to, once again, modify this. Once again, the same error is also here. So let's put it as 3. Right, so this is, yeah. So this is how the others are computed. Like, as I was mentioning you, that how these are computed, these components are computed. There, it is the gradient of the function multiplied the corresponding weight, because this is coming from this part. So that multiplication and this function. So this, suppose this is y23. So the gradient of this function, which is in this case, as you know, that if all the function are same, we keep all the nonlinearity functions same usually in the artificial neural network. So that's why we are always writing a prime of the whatever the value, input value is there, that is the gradient. And then z23, this derivative of this, so that means this weight should be coming here. So that is why you can see that W1, 2, 3. So this weight is denoted in this form. Okay, so you are denoting in this form. This weight is W1, 2, 3. So you are multiplying this. In the same way, you are doing this. So we write it in this form, and this is how the computations are carried out. And interestingly, no, we can consider, as you can see there, what we are doing in the back, we are making it but bit systematic. So at the, when you are computing the for example, the effective cumulative gradient value at this point, which in the chain rule, then it has to be multiplied by the subsequent part. At that point, you are adding all these gradient values. So these are called, these are called, so at every node, what is the effective cumulative gradient is accumulated, and then for the other nodes, at the other nodes, what we are doing, we are simply multiplying the, it is basically weighted summations, weighted by the corresponding age weights. So at this point, say it is, say, delta 1, 1, 3. So say at this at this age, so it is basically delta 1, 1 with respect to this. It is delta 1, 1, 3, and it is multiplied. Actually, you can call also delta 1, 3 at this point, and then you multiply with W113 this way. Similarly, here it is delta 1, 2, 3. So because it is 1, 2 node, or you can call it delta 2, 3 also, and then you multiply by W1, 2, 3. So that is the that is called delta rule, because you are accumulating the deltas, that means the gradient values at every node, and then these gradient values are weighted. You make a weighted sum of those gradient values, which are connected to the to the output of the node of the previous layer. And in this way, using delta rules, you go on accumulating the gradient values at each node. So that is how you are doing it. So you are basically, you are considering those components as delta 1, 1 propagated along that edge. That is how this convention is used. So this is also shown here. This process, what I mentioned, delta rule. So at the ith layer, you are accumulating these delta values, and then you make the weighted sum of those delta values, and then accumulate to the other node. And in this way, you process. And at the finally, what happens, that for a particular parameter, there you multiply with the input. At that point, you multiply with the input. So that is how you get the corresponding gradient part or partial derivative part for that parameter space. So this is the essence of this backpropagation algorithm. This is how you compute the partial derivatives for each component, and you can perform these operations. You can compute for each one. So finally, from the overview, if I give an overview, so in the heart of the technique, this backpropagation algorithm is used for computing the gradients. But once you get the gradient, then the normal training, I mean, the optimization issues, optimization procedure is the same, because you will be moving towards the opposite directions of that gradient direction with certain step size, and update the weights, and you go on doing these things till you get a convergence. So you are doing these things. Now there are some tricks when you are considering the no when you are applying this process, or when you are doing the optimization, there could be some kinds of problem would be there, that as you can see, that gradients may change abruptly in consecutive iteration, and then the convergence would be an issue. So what you can do, that you can consider that instead of using simply the gradient values, you can use certain kind of running average of whatever the previous gradient value and the new value. So you take the running average of that, and that you are using. So you consider this parameter as a momentum parameter, and there you are using it. Otherwise, the other method could be that you can use some adaptive learning rate when you find that so learning rate can be you can increase learning rate at constant steps if error decreases, and you can decrease it otherwise you geometrically. That means the learning rate also can be at the point of convergence, learning rate should be small. I mean, slowly you are decreasing the learning rate, and when there is learning rate tends to 0, means you are not learning further, and that itself will give you a sense of convergence. So these are certain things which are also used in this process. So just to summarize, I mean, that is the essence of the artificial neural network, and you know that various optimization tools are also available. There are other optimization techniques you can use, and there are various other variations. So which we are not discussing here. I have just given you the basic concepts involved in this particular process, particularly the backpropagation, which is very popular in this process. So just to summarize, a perceptron, we have seen the neural network, artificial neural network, is actually the network of perceptrons, what we discussed, which models a linear discriminant classifier, a two-class linear discriminant classifier also. And it's a very powerful model. We discussed about the multi-layer feed-forward network and the backpropagation algorithm, but there are other kinds of connectivities are there, where even the network with the feedbacks, all those neural configurations are also there. So you need to make advanced study to understand them. And the highlight is that, as we have just discussed, see, we can consider it as a classification problem, or we can consider also standard regression problem. So in the classification problem, the values are discrete, labeled with the classes, whereas or kind of states, you are trying to achieve a states. So you have to take certain decisions. In the sigmoid function, you have to take a decision that when you are considering which class it is, and there are certain probabilistic interpretations which I did not put forward here, as we have discussed earlier also, that actually sigmoid is the inverse of logits. So which means it directly gives you a kind of posterior probability. So you can have those interpretations. You can have those interpretations. You can use softmax probabilistic interpretations to make it a probabilistic interpretation. So those are used in the neural networks. Particularly in deep learning, we know that those are used very much. So you can also use it as a regression. So there are various ways you can interpret the outputs, and the various kind of tasks that you can perform by these models. So with this, let me stop here today. And if you have any questions, let me know. Okay, just to remind you that on Wednesday,